Good morning. We have been discussing different models of surface patches. Just a little recap on what we did last time. We studied Ferguson's patch in quite some detail. So the mathematical expression for the patch is R of U and V is given as the row matrix phi 0, phi 1, phi 2 and phi 3, all functions of parameter u, times the geometric matrix, I'll come to that a little later, times the column vector phi 0, phi 1, phi 2 and phi 3, all functions of parameter v. These phi's happen to be cubic Hermite polynomials, as you would know from Ferguson curves. This geometric matrix here, you can think of subdividing this into 4 parts. Draw a vertical line here and draw a horizontal line here. This part here contains the point information evaluated at u equals 0, v equals 0, u equals 0, v equals 1, u equals 1, v equals 0, and u and v both equal to 1. This region here comprises information pertaining to the slopes along the v direction, r sub v, which is also partial r over partial v. Again, evaluated in the same order as these 4 numbers. The bottom left region comprises of the slope information along the u direction, r sub u, or partial r over partial u, evaluated at 0, 0, 0, 1, 1, 0 and 1, 1. Finally, the bottom right portion here comprises of twist vectors given by the mixed derivative, the mixed second derivative of r with respect to parameters u and v. We had mentioned last time that as a designer, it is not very straightforward for us to provide higher order information. For example, slopes along the respective parameter directions and the twist vectors. That is one prime motivation as to why we would want to consider surface patch models that involve specifying only data points. Nevertheless, we looked at 2 examples last time, one corresponding to this geometric matrix where the twist vectors were specified 0 and the slopes along the v parameter direction and the slopes along the u parameter direction were specified arbitrarily. This is the result that we got for this geometric matrix. And if we specified the twist vectors to be non-zero and arbitrary, for example, through this geometric matrix, we got a significantly different result. The point that I am making here is that it's not intuitive for us to predict shape changes if we specify the slope and the twist vector information in different ways. Today, we are going to be looking at tensor product surfaces that use data point specification. This is lecture number 37 on tensor product surface patches. The first model is the 16-point form surface patch. Mathematically, the model is expressed as R as a function of parameters u and v is equal to summation index j going from 0 to 3, again summation index I now going from 0 to 3 times d sub ij times u raised to I times v raised to j. In matrix form, this can be written as a row matrix comprising u cube, u squared, u and 1, a geometric matrix with coefficients d33, d32, d31, d30 as the first row, d23, d22, d21, d20 the second row, d13, d12, d11 and d10 for the third row, and finally in the last row d03, d02, d01 and d00. This is to be post multiplied by a column vector comprising different degrees in v. V cube, v squared, v and 1. It is this geometric matrix that we need to determine. We'll see in a while how. Let me emphasize that parameter values u and v both range between 0 and 1. To be able to determine what dij's can be, let us subdivide each interval 0, 1 as 0, 1 over 3, 2 over 3 and 1, and try to sample data points at these parameter values. Okay, so the idea is that we have 4 values for parameter u, 0, 1 by 3, 2 by 3 and 1, and likewise we have 4 identical values for parameter v. Correspondingly, we will be having 16 sample points that we would need to use to determine the unknown coefficient matrix. Geometrically, this is how the sampling data would look like. We will require point information pertaining to R00, R1 over 30, R2 over 30, R10 for values of v as 0 and for different values of u along this curve, and then R0 1 over 3, R1 over 3 1 over 3, R2 over 3 1 over 3 and R1 1 over 3. The ninth data point or sample point will be R0 2 over 3, R1 over 3 2 over 3, R2 over 3 2 over 3 and R1 2 over 3. The final 4 points will be sampled at values of u as 0, 1 over 3, 2 over 3 and 1, and the values of v at 1, 1, 1 and 1. So if you notice, these are 16 sample points on the surface patch that we'll be using to determine the unknown coefficient matrix Dij. So this is the same patch with the notations removed. So if you notice here, this matrix is the sample point matrix we'll be using to determine Dij's. R33 is R11, R32 is R12 over 3, R31 is R11 over 3, R30 is R10. Correspondingly, R23, R22, R21 and R20 are sample points for values of u as 2 over 3 and values of v as 1, 2 over 3, 1 over 3 and 0. R13, R12, R11 and R10 again are values for u equals 1 over 3 and for v going from 1 to 0 uniformly in 4 steps. Let's assume that we know the geometric information encapsulated within this matrix. So essentially, we know the 16 sample points on the 16-point form surface patch. This would be equal to this 4 by 4 matrix here with elements 1, 1, 1, 1, 8 over 27, 4 over 9, 2 over 3, 1, 1 over 27, 1 over 9, 1 over 3 and 1, and 0, 0, 0, 1. Now if you notice, each row from left to right would correspond to powers of u cubed, u squared, u and 1. The first row corresponds to u equals 1. The second row corresponds to u equals 2 over 3. The third row is for u equals 1 over 3. And the fourth row is for u equals 0. And then we'll have this 4 by 4 unknown coefficient matrix. And again, we will have a 4 by 4 matrix corresponding to different powers of the second parameter v, arranged column-wise. The first column here corresponds to 1. The second column here corresponds to v equals 2 over 3. The third column corresponds to v equals 1 over 3. And the fourth column is for v equals 0. The first row relates to v cubed. The second row corresponds to v squared. The third row is for v raised to 1. And the fourth row is simply 1. So what is the situation now? We have this geometric sampling information on the left-hand side. We know what this matrix is. We know what this matrix is. All we need to do is we need to pre-multiply this matrix on the left-hand side by the inverse of this matrix here. And we need to post-multiply the result here by the inverse of this matrix to get the unknown Dij's. Okay, let's continue. So the unknown coefficient matrix Dij will be given as M16, I'll tell you what this is in a while, times the sampling geometric matrix times M16 transpose. what is M16? M16 is given by the inverse of this 4 by 4 matrix, 1, 1, 1, 1, 8 over 27, 4 over 9, 2 over 3, 1, 1 over 27, 1 over 9, 1 over 3, 1, and 0, 0, 0, 1. One thing that you would want to realize, and this is interesting, is that I'm using the transpose of M16 here. Why is that? Let's go back and try to investigate these two matrices. M16 is the inverse of one of these matrices. And if you look at this matrix here, this is nothing but the transpose of this matrix. One reason why we use the transpose of M16 here. Nevertheless, with the sampling information available to us, we can identify the unknown coefficient matrix Dij, and once we have that, we have the mathematical expression for the 16-point form surface patch. The discussion about this type of tensor product surface is kind of academic. I'm not quite sure if the CAD industry uses this model often. Rather, the industry uses Bézier surface patches and B-spline surface patches more commonly. So finally, the 16-point form patch looks like R as a function of u and v equals u cube, u squared, u1, the row matrix, times M16 times the sampling information that we provide to determine the unknown Dijs, times M16 transpose times the column vector v cube, v squared, v, and 1. Let's move on now to more commonly used patch models. The first one of those is the Bézier surface patch. 10 marks for guessing this. How would the mathematical form of a Bézier patch look like? Well, think about it. It would be using Bernstein polynomials. Bernstein polynomials as functions of u and v independently. Okay, so the patch as a function of u and v will be given by summation index I going from 0 to m, index j going from 0 to n. These are two different degrees along u and v respectively, times r sub ij. This is where the designer would come in picture. He would specify the x, y, and z coordinates of each design point r sub ij times the Bernstein polynomial with index j and degree n as a function of v, and another set of Bernstein polynomials b with index I and degree m in parameter u. So, if the designer specifies a bunch of design points or control points the patch is readily available. We don't need to go through computations that we saw in the previous patch model, the 16-point form surface patch. As I said, R sub ij, where index I goes from 0 to m and j goes from 0 to n, are the control points or the design points. BIMs and BJNs are Bernstein polynomials in U and V. In compact matrix form, R of U and V is given as the row vector with u raised to m times u raised to m minus 1 times 1 minus u, and so on, with the last term as 1 minus u raised to m, times the geometric matrix, the first row being R 0 0, R 0 1 up till R 0 n minus 1, R 0 n, R 1 0, R 1 1. The last but one term in the second row will be R 1 n minus 1, and the last term will be R 1 n, and so on until we consider the last but one row with entries R m minus 1 0, R m minus 1 1, R m minus 1 n minus 1, R m minus 1 n, and the entries in the last row will be R m 0, R m 1. The last but one entry in this row is R m n minus 1, and the eventual entry is R m n. And of course, we'll have the corresponding column vector where we place Bernstein polynomials in V. Now, could you guess what the properties of the Bézier surface patch would be like? While discussing Bézier segments, we had extensively studied the properties of both Bernstein polynomials as well as Bézier curves. If you think about it, all those properties will be inherited by the Bézier surface patch models. Let's take an example of a bicubic Bézier surface patch. Here you will have degrees 3 in both U and V. So the mathematical expression is given by R of U and V equals the row vector U cube 3u squared times 1 minus u, 3u times 1 minus u squared, 1 minus u cube, the geometric matrix that will be now given by 16 design points arranged nicely along the parameter directions u and v, and we'll have Bernstein polynomials of degree 3 as a function of V arranged in the column form here. If you do a bit of algebra, you can replace this row vector by u cube, u squared, u and 1 times the Bézier coefficient matrix, if you remember, with entries -1, 3, -3, 1, 3, -6, 3, 0, -3, 3, 0, 0, and in the last row 1, 0, 0, 0 times the geometric matrix here times the transpose of this Bézier coefficient matrix times the column vector v cube, v squared, v and 1. This is equal to u cube, u squared, u 1 arranged row wise times m sub b times the geometric matrix times m sub b transpose times v cube, v squared, v and 1 in column form. MB, as I mentioned earlier, is this 4 by 4 matrix here. Bicubic Bézier surface patches control polynet or control net. This is how your polynet or net will look like. So a user will be specifying 16 data points, and the corresponding bicubic Bézier patch will be observed like this, with these 4 as bounding curves. This could be boring, but let me go through the nomenclature of these design points again, because as a designer, the order in which these design points are specified can be important. So the first point is R00, R01, R02, R03. So this curve here corresponds to the u value equals 0 and the v value progressing from 0 to 1. This point here is R10, R11, R12, and R13. This is R20, R21, R22, R23. Finally, R30, R31, R32, and R33. Let's now pop up the mathematical expression for the Bézier surface patch model. Here m equals 3 and n equals 3. And whatever we have learned from our previous discussion on Bézier segments, let's try to use them to understand how we can predict the shape of a Bézier surface patch via the shape of the corresponding control polynet. Okay, take a look at this control polyline R00, R10, R20, R30. This would correspond to the parameter value v equals 0. So these are the 4 bounding curves. This curve here is for v equals 0. Now, what do you have to say about the shape of this curve? Well, think about the partition of unity property of Bernstein polynomials that gives rise to the convex hull attribute. What do I mean? Well, this curve is going to be lying within the convex hull given by these 4 design points. Also, the shape of this curve will be loosely predicted by the shape of this control polyline. Let's take a look at another bounding curve. This one, for example. This curve corresponds to the value of v equals 1. We have the control polyline given by R03, R13, R23, and R33. Once again, this curve will lie within the convex hull given by these 4 design points, and the shape of this bounding curve will be predicted not strongly but loosely by the shape of this polyline. What do you have to say about the nature? Let me be a little precise about the mathematical nature of these 2 curves. Now, this corresponds to v equals 0. This corresponds to v equals 1. Would you agree with me that these are 2 cubic Bézier segments? Think about it. Likewise, how about these 2 bounding curves? This one here corresponds to u equals 0, and for different values of v in between 0 and 1. Correspondingly, we have this control polyline. Because of the partition of unity property or the convex hull property, this curve will lie within the convex hull of these 4 points, and the shape will be predicted by the shape of this polyline. And the same is true for this bounding curve here, for u equals 1 and v ranging from 0 to 1. In fact, all of these 4 bounding curves are Bézier segments, each of degree 3. How about the shape of the surface patch overall? Let's look at this expression here. So the product b sub I m of u and b sub j n of V acts as the weight corresponding to the design point Rij, would you think these weights will also be barycentric in nature? So this is the expression for the tensor product surface involving Bunstein polynomials. R of uv is equal to summation I going from 0 to m, summation j going from 0 to n, the design points Rij times the Bunstein polynomial with index I of degree m in U and the Bunstein polynomial with index j and degree n in V. We need to show whether this product is barycentric or not. So first we realize that B I M U is equal or greater than 0, and also Bj n V is equal or greater than 0 for values of u in between 0 and 1 and for values of v in between 0 and 1. Clearly, the product Bim u times Bj n v will be greater than equal to 0. This is for u and v both belonging to the interval 0, 1. Next, to show that this product is barycentric, we need to show that summation I going from 0 to m, summation j going from 0 to n, B I M U B J N V equals 1. We show this now. So we have 1 minus u plus u raised to m equals 1. Also we have 1 minus v plus v raised to n equals 1. We multiply both these equations together to get 1 minus u plus u raised to m times 1 minus v plus v raised to n equals 1. From our discussion on Bézier segments, we know what this binomial expansion is. So for the first case, we have B0 m u plus B1 m u up till Bm m u times B0 n v plus B1 n v up till Bn n v equals 1. You would have realized that the Bunstein polynomials form individual terms in this binomial expansion, and Bjn of v, all of these terms over here, are individual terms appearing from this binomial expansion. We can write this equation in short form. summation I going from 0 to m bi m u times summation j going from 0 to n b j n v equals 1. I can bring this summation sign here, and I can get summation I going from 0 to m summation j going from 0 to n b I m u b j n v equals 1. Let's block this result and let's block this result here. These results, when combined together, make the product of two Bernstein polynomials barycentric. Since the bicubic Bézier patch, or any Bézier patch for that matter, is derived from the corresponding Bézier curve models by use of Bernstein polynomials, all the associated properties get inherited. From the design viewpoint, this means that this patch will be lying within the convex hull defined by this control net. Also, the shape, the overall shape of this patch will be controlled loosely by the shape of the net. In a sense, if I move, for example, R12 to a different location, the corresponding portion on the patch will get changed in shape accordingly. However, the shape change will be global. That is, the change will persist in the entire patch as opposed to it being local. As you know, Bernstein polynomials are barycentric, but that's not a local property, as we have seen in case of B-spline basis functions. Rather, if we use B-spline basis functions over here in place of Bernstein polynomials, and we'll be studying these models later, the corresponding shape changes will be local. Another example, we can say fuse these points together to get a triangular patch. Why? Because since this bounding curve lies within the convex hull of this polyline, fusing these points together will make this curve become a point. And as a consequence, we will not have 4 bounding segments, but rather 3 of them. Let's take a look at a few examples. The first one, the control points for a quadratic cubic Bézier patch are given by 0, 0, 0, 1, 0, 1, 3, 0, 1, 5, 0, 0, 0, 2, 0, 1, 3, 1, 5, 1, 1, 6, 1, 0, 0, 5, 0, 1, 4, 2, 9, 2, 3, 8, 2, 0. Here m equals 2 and n equals 3. Corresponding to u, we'll have Bernstein polynomials of degree 2, and corresponding to parameter v, we'll have the same in degree 3. We can do the math and get the x, y, and z coordinates in terms of u and v. To get the x coordinates, we use the first set of values. For the y coordinates, we use the second set of values. And to get the z scalar field, we use the third set of these values. Let's try to figure how the surface patch looks like. For this geometric matrix, this is how the patch appears, and this is the control polynet in black. The patch is shown with 3 different view directions. This is the top view. If you recall our discussions on transformations, from here to here to here, we are essentially performing a few of them. If we change the control point R10 to 5 to 10, a different surface patch will result. That is shown here, again, via 3 different views. The second example. Now this is for a bicubic Bézier patch. The control points are given as 0, 0, 0, 1, 0, 1, this is R10, 2, 0, 1, R20, 3, 0, 0, 0, 1, 1, 1, 1, 2, 2, 1, 2, 3, 1, 1, this is for R31, 0, 2, 1, 1, 2, 2, 2, 2, 2, and 3, 2, 1. And finally, R03 is 0, 3, 0, R13 is 1, 3, 1, R23 is 2, 3, 1, R33 is 3, 3, 0. With this geometric information, the patch looks something like this. The control polynet or the control net is shown using lines in black. If we change R11 to, let's say, 2, 3, 2, and if we also change R21 to, let's say, 4, 7, 4, we will witness a shape change in the patch, and that change, as I mentioned earlier, will be global. How to get a triangular bicubic Bézier patch? We'll have to collapse the data points or the design points for any bounding or boundary curve to create a triangular patch. So this is the information that we had from the previous example. And if R00, R10, R20, and R30 are all collapsed to a point 100, this is the triangular patch that we're getting. These are 2 different views. And you can clearly observe that we have now 3 as opposed to 4 bounding curves. Finally, we come to B-spline surface patches. The mathematical expression is given by R of u and v is equal to summation I going from 0 to m, j going from 0 to n of Rij times n p plus I as a function of u times n q plus j as a function of v. What have we done here? We have simply replaced the Bernstein polynomials in Bézier surface patch with the corresponding B-spline basis functions. Corresponding to the indices I, np p plus I are basis functions of order p, and corresponding to indices j, nq plus j are basis functions of order q. In general, p may not be equal to q. The two orders along the parametric directions u and v can be different. Like in case of Bézier surface patches, we can also argue that this product is now locally barycentric. I emphasize locally barycentric. What do I mean? Each of these individual terms, np p plus I of u, is equal to or greater than 0. Likewise, nq q plus j of u is equal to or greater than 0. Correspondingly, this product will either be 0 or positive. Further, from our discussion on B-spline basis functions and segments, we know that p of these order p basis splines sum to 1. That is, np I plus 1 of u plus np I plus 2 of u up till np I plus p of u is equal to 1 for values of u belonging to the interval ui plus 1. These are the knots in the parametric value u. Likewise, q of these order q basis spline functions will also sum to 1. That is, nq j plus 1 of v plus nq j plus 2 of v up till nq j plus q of v is equal to 1 for values of v in between vj and vj plus 1. Again, these are the knots in the parameter value v. Like we showed in case of Bernstein polynomials, we can also observe that the product of these B-spline basis functions will sum to 1 in some region. And this is the property that provides local shape control to B-spline surface patch. If you understand our discussion on B-spline basis functions, you will not have much difficulty comprehending this property. You would also observe that strong convex hull properties are inherited by B-spline surface patches. For some region R, which is a product of these two intervals ui plus 1, vj plus 1, all we need to do is we need to alter or relocate the control points Ri minus p plus 1, Ri minus p plus 2 up till Ri, or Rj minus q plus 1, Rj minus q plus 2 up till Rj to observe or witness local shape changes. Let this be an exercise for you to figure how many knots will be needed corresponding to parameter u and those corresponding to parameter v. Although I will not discuss B-spline surface patches further. You're free to explore these models in detail all by yourself.